Good afternoon, folks. How are you today? In my last lecture, I had a small error in my video presentation. In some of the frames, I may have mentioned that alpha goes from 0 to 2. That is not the case. You may remember that alpha was equal to volume of water divided by volume of tank. And obviously, there can be no water. To maximum we can have is as much as the tank. So alpha goes from 0 to 1. On the other hand, x was defined as h over r. So again, h can be 0, but maximum you can see that once the tank is full, h can be equal to 2r. So x can go from 0 to 2. Now what you will be doing in lab number 3, you'll be doing the same exercise that I did, except that you will have a spherical tank. So we'll talk about it in lab number 3. Okay, let's talk about error propagation during arithmetic operations. So you will find, and I'm just stating this, that in addition or subtraction, basically we try to preserve the number of correct decimal digits. So if we are adding two things, our result will have whichever of the two inputs has lesser precision. When we are multiplying or dividing, we essentially preserve the number of significant digits. So if we have two numbers that we are multiplying or dividing one by, then our result will have whichever one has lesser precision in terms of significant digits. So we are going to look at error propagation using calculus principles. Before we get into more involved thing, let's look at addition or subtraction. So let's suppose we are given two numbers, A and B, and we want to perform either addition or subtraction. So if we take derivative of this, we will know that partial derivative, we will get delta A plus minus delta B. Now when we think of errors, we normally don't pay any respect to the sign. So think of it as we are just taking magnitudes, and of course we don't want to cancel errors. So our result would be delta Z is delta A plus delta B. Doesn't matter whether we are adding or subtracting. And you can see that these are related to correct decimal digits. So we are basically adding absolute error bounds. So let's see some examples. Let's suppose our A was 0.1235 plus minus 0.0002. So we had 3 to 4 significant digits. Let's say B is 0.1234 plus minus 0.0001. Same 3 to 4 significant digits. So let's do addition operation. Z is A plus B. So we add these two numbers. And we get 0.2469. Now we also just derived that delta Z is delta A plus delta B. So that will come out to be 0.0003. So you can see that absolute error bounds added up. Now, in terms of percent error, let's calculate percent error. 0.0003 divided by 0.2469 times 100, and we round up, so we get 0.2% error. It's error bound. Okay, let's look at subtraction. So we subtract a minus b, we will get 0.0001. Now delta z remains the same, delta a plus delta b. So that's 0.0003 still. So let's calculate percent error here. So we'll have 0.0003 divided by 0.0001. So that's 300% error. Wow. So we have a problem. Whenever we are subtracting nearly equal numbers, we can get a huge loss in precision. Okay. Let's see multiplication. So we take partial derivative. So we'll first take derivative with respect to a. So we'll have just b. So we'll write b times delta a. Plus, now we'll take partial with respect to b. So we'll have a times delta b. Remember always that we are talking about magnitudes. So that's our result. An interesting part here, just we are going to calculate this in a moment, but let's divide everything by z. So then we'll divide this by a times b, divide this by a times b. So we will get delta z over z is delta a over a plus delta b over b. So the interesting part here, when we multiply, is now the relative error bounds add up. So let's go back to our example and just for simplicity, I'm going to repeat. A was 0.1235 plus minus 0.0002. B was 0.1234 plus minus 0.0001. So let's do Z is A times B. So when we do A times B, we will get 0.1235 times 0.1234, and we will get 0.01524. We'll keep 4 digits. Okay, from our previous derivation, we had found that this was B times delta A plus A times delta B. So let's calculate this. So we'll have 0.1234 times 0.0002 plus 235 times 0.0001, and we will get 3.7 times 10 to the minus 5. So let me kind of write it as point. So we will have 4 of these zeros, rounded up would be 4. So let's see how much percent error we have. times 100. So we have rounded up 0.3% error. So remember, this one had 0.0002 divided by 0.1235 times 100. So this one has 0.2% error. This one has 0.1% error. So you can see 0.2 plus 0.1, 0.3% error total. Okay. We would have found the same thing if we had done delta Z over Z is delta A over A plus delta B over B, right? Now, same thing. So we will get 0.0002 divided by 0.1235 plus 0.0001 divided by 0.1234 times. So this will be 0.003, which is 0.3% error. Same thing we calculated. Okay. All right. Let's try division. Z is A divided by B. So we'll calculate delta Z. First, we will find derivative with respect to A. So we'll have 1 over B times delta A. Then we will find derivative with respect to B. So we'll get minus A over B square times delta B. Just again, we are going to calculate delta Z in a moment. But let's divide everything by Z. So we are going to divide this A by B, divide this A by B. So interestingly, we'll get delta Z over Z is again delta A over A plus delta B over B. So in division again, relative error bounds add up. Let's go ahead and do our calculation. So again, repeating the numbers, A is 0.1235 plus minus 0.0002. B is 0.1234 plus minus 0.0001. So Z, which is A divided by B, is 0.1235. So rounded up, we'll get 0.101, 4 digits. All right, let's calculate delta Z. So it was 1 over B delta A plus A over B square, I've thrown out negative sign, delta B. So we have 1 divided by 0.1234 times 0.0002 plus 0.1235 divided by 0.1234 square times 0.0001. So again, we will get 0.003. So if we look at delta Z over Z, this is like 0.3% error. So remember, this was 0.2% error. This was 0.1% error. So when we do division, these relative errors add up. Okay. So we will find out when we do delta Z over Z is delta A over A plus delta B over B. So you calculate that and you'll find out, rounded up, it'll come out to be 0.003. Okay, so we did some simple arithmetic operations and we see the ideas. What happens if we do some more compound operations? So let's suppose Z is a function of many variables. A has uncertainty delta A, B has delta B, so on. So we want to calculate what is the uncertainty in Z. So what we do is we take partial derivative with respect to A, multiply by delta A. Partial with respect to B, multiply by delta B, and so on and so forth. So let's take an example. Let's suppose our function was A minus B times D. So the simplest way is to make a table. So we do del Z, del A. So partial derivative. So we have A times D, partial derivative is D, minus B times D, there is no A in it, delta Z over delta B, A times D, no B in it, minus B times D, we differentiate, we will get minus D. Then delta Z over delta D is A minus B. Okay. So our delta Z would be D times delta A, partial derivative D times delta B, partial derivative of this times delta D. So this is how we'll calculate. So let's say we have our numbers again. A is 0.1235 plus minus 0002. B is 0.1234 0001. And let's choose D. I'm going to choose D as 0.5678 plus minus. Let's choose this to be 0.0012. Okay. So we calculate Z is A minus B times D. 235 minus 0.1234 times D 0.5678. So I get 0.5678 times 10 to the minus 4. Let's calculate delta Z. So using this table, we know D is 0.5678, 0.5678, 0.0001. So our delta Z would be 0.5678 times delta A. 0.5678 times delta B. 0.0001 times delta Z. and we'll get 1.7 times 10 to the minus 4. So let's see what is our delta z over z. This has 300% error. What happened? The reason we got was a minus b potentially had 300% error, and in multiplication we preserved it. So we got to be very, very careful whenever we are subtracting two nearly equal values. And it can be anywhere in our compound operation. So again, want to emphasize, don't subtract a nearly equal value. Now, also when you're subtracting or adding huge number of small values, think of adding or adding negative numbers instead of calling subtracting. So you're adding a huge range of values. Let's just simply assume they were all positive values. If they were all positive values, let's say they range from very, very small 0.0001 to huge like 10 to the power 6. So what happens is if they are arranged randomly, and let's suppose you start having 10 to the power 6, even if you add a lot of 0.0001s to it, 10 to the power 6 is not going to change. So what you want to do is you want to sort your values from small to large in magnitude before you add them up. Otherwise, you're going to lose precision. So this is again some of the things that packages like MATLAB, etc. may miss, and you may have to therefore massage your data. That means sort the values if you think MATLAB might be summing up huge number of values. And of course, we have talked about division by zero. You have to be attentive. If there is a potential for division by zero, you need to decide what needs to be done. So we have talked a lot about finding root of a function, significant digits, precision, talked about computer architecture. I want to talk about two spacecrafts, Voyager 1 and 2. These were twin spacecraft. They made basically two identical spacecrafts, and they were launched in 1977. This sticks in my mind because I came to US in 1976. I was a graduate student, and I was very, very impressed by what was being done in design of Voyager 1 and 2, and I was really very excited about it. Just to let you know, 50 years later, almost, they are still working and sending data. Voyager 1 flew to Jupiter and Saturn before leaving the solar system. Voyager 2 also flew to Jupiter and Saturn, then its path was modified to include Uranus and Neptune, visited both before it left the solar system. Still working, sending data. So let's look at their computer. Each of these spacecrafts had three pairs of computers, one being redundant or backup. They had very low power usage, so you can see they are still continuing to operate, send data. Their fastest computer was only 80,000 instructions per second. That's 80 times 10 to the power 3, and we call this floating point operations per second. So this is kind of very, very slow microprocessor. Even your phone, just in comparison today, would have at least a power of something like 1 giga, which would be 1 times 10 to the power 9 operations per second. They had complicated architecture, but again, very rudimentary architecture, 4-bit, 12-bit, 18-bit registers. Probably the first computer you started it with was 32-bit already, and you are seeing already in the last 5 years, now the standard computers are 64-bit computers. So their word length is 64. Memory, each of these computers had only 64K bytes. 64K bytes. Imagine. Today you have a phone. I'm sure your phone has at least 8 gig. So that's like 8 times 10 to the power 9 bytes of memory. Can you imagine this? A million times more. So I just want to let you know what you could do with your power today when they could do wonderful things 50 years ago with this rudimentary computers. Okay, folks.